Thank you to the Secretariat for allowing me to do this presentation to both the Asia-Oceania and America's Floods Working Group for EOTech DevNet. My name is William Straka, and I'm from the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin-Madison. I have several co-authors here that are integral in leading and developing the NOAA flood algorithms that we're discussing here. So first, I'm going to give a brief overview of the CEOS Working Group for Disasters, and then give some examples of the current and future global flood inundation mapping systems. The CEOS Working Group for Disasters Flood Pilot Project is to explore and demonstrate best practices from combining diverse optical and SAR data into map floods, and then record these best practices developed through the integration of LEO, GEO, and SAR. Although this is still sort of a relevant objective, the motivations, behind this are to gradually transition exploring the use of the satellite Earth observing data to other aspects of flood risk assessment and management. There are many different subgroups within the CEOS Working Group for Disasters Flood Pilot Project. There's the Red River in the north in the United States, led by Vince Decker. Then in Argentina, led by Marcelo Cone, as well as several in the Asia-Oceania region, from the Pearl River in China, and of course, flood regions in India, and flooding in the Myanmar region. We also do have a project along in the Balkans, exploring the data there. There's a variety of aspects being covered in the subgroup. Again, like I said, merging various data sets together, using machine learning techniques to merge the water fraction projects, downscaling digital elevation models so that we get data at higher resolution, infusion of satellite data into flood monitoring and warning systems, and automated flood extent mapping systems. Going into optical flood products, people may be familiar with these. They use data from the visible, near infrared, and shortwave infrared channels, along with a series of tests to combine them, along with water reference maps, which discriminate permanent water bodies. And this is in use to create a fraction of a pixel that is flooded, or where a pixel is flooded and where it is not. We're able to combine data from geostationary imagers, such as the Advanced Baseline Imager on the GOES series of satellites, or the Advanced Himawari Imager on the Himawari series of satellites for the Asia-Oceania region, to create a daily cloud-cleared flood product. One can also use digital elevation models and other high-resolution data sets to create flood depths at higher spatial resolution, so down to 30 meters. These are different from RGB composites because a flood extent map gives a quantitative measurement of how much of a pixel is flooded. This can then provide stakeholders a method to exploit other data sets, croplands, population data sets, to determine the impacts from a flood event. The disadvantage, of course, of optical products is that they're limited to cloud-free and daytime conditions only. But they do have the advantages of providing excellent data availability with large spatial coverage and at low cost. Currently, the NOAA VEERS flood product is produced operationally, and the geostationary products from both ABI and AHI are being transitioned to operations. The geostationary from AHI actually will be run operationally by the Australian Bureau of Meteorology, which is doing that transition. And of course, the geostationary ones over the United States and North America will be done by NOAA. So this is an example of the 5-day flood inundation map. What's done here is we take all of the data from a given day from our low Earth orbiting satellites, with the optical sensor on there. We create a cloud-free daily composite to get a maximum flood extent over a region over the current day. We then can take 5 days worth of data and get that maximum flood extent over the last 5 days. This is particularly important because low Earth orbiting satellites don't necessarily have cloud-free days all the time. So to get a maximum flood extent, that's important to get the maximum impact. Some examples of actually the utilization of the NOAA flood products have been through UNISAT with the United Nations in producing their flood extent and population impact and cropland impact analyses, as shown here from Pakistan from 2021. And this is done from data from the 1st of July all the way through the end of August. So they're taking several months of data and getting that maximum flood extent for those 2 months of data sets. And they're also combining that not only with population and cropland impacts, but also other optical satellite data, as can be seen here and here. But there's also key information on the amount of impact that is being done. Synthetic aperture radar products provide very high resolution flood mapping, though at a lower temporal resolution. Or they have the advantage to be able to see flooding at all times during the day, whether that's daytime, nighttime, cloud covered, cloud free. So similar to what happens in the optical flood algorithms, the transmitted radar data signals on flat water surfaces are reflected back with a significantly weak signal back to the satellite, which is then detected. There are quite a number of satellite missions that are available. Sentinel-1, the radar constellation mentioned, RadarSat-2, the JAXA AOS satellites, and many others. However, most of these have very low repeat cycles and are often restricted data sets. In addition, most SAR products are actually these RGB qualitative type products, which delineate the flood, no flood by simply different colors. But there are several SAR flood products that are quantitative, that are being produced or being developed by various agencies, such as NRCan in Canada, Copernicus EMS, NOAA NESDIS, and the National Water Center at NOAA. This is an example of the pre-operational developmental algorithm being done by NOAA and the University of Wisconsin in Milwaukee, called RAPID. And it takes data from C-band radars, so that's RadarSat Constellation, Sentinel-1, RadarSat-2. As can be seen in the animated GIF, you're getting the same amount you're getting lots and lots of passes over the Red River from multiple types of satellites. So each of these can be used to develop a flood extent, such as this one from the 29th of April last year. And then, in addition, taking a digital elevation model, we can begin to look at flood depth, which is very important for impacts on crops. Because if your flood is over a cropland and it's too deep for a long period of time, it can have extensive impacts on the crop growth and the like. This is, again, just some more examples from the SAR algorithm, this time over Pakistan from 2022. As you can see, Fears was clouded over, but there was a SAR pass right over the area where there was flooding. And what we can do is we can take these two data sets and now merge them into a best of flood data set, in this case, solely the SAR data, and then provide this data to stakeholders when the area is cloudy. Again, another example of this where we have, again, it's cloudy over Pakistan. You can have the SAR products getting the upper parts of the river. But there is some information down along the coastlines, which the SAR products do not get. And this can be seen in and even up here in some of the areas in the upper reaches of the river basin there. And then by merging, we can now get this a more accurate picture of what's going on in the region. So again, combining the data sets. Again, this is very preliminary. The results are very promising. I mentioned downscaling using digital elevation models. The NOAA products are currently taking that 375 meter product and downscaling using the 30 meter digital elevation model from the Copernicus mission, which then produces a much more accurate picture of where the flooding has occurred as compared to some other DEMs, such as the SLSTR, which was developed during several space shuttle missions. Again, going back to the blending of the products, again, you can kind of see, again, this is another example where we actually have a clear sky veers, because a SAR pass again on the same day, and then now we get an even more accurate picture. So again, this is what will enhance the flood product by providing the highest resolution flood maps, as well as flooding under cloud or at night. Future efforts that NOAA is doing is exploring the use of L-band radars, such as the NISAR satellite, which is a joint NASA-ISRO satellite, which is to be launched early this year. SAOCOM, Roselle, and Aeolus 2 and 4. So many different, adding in more satellites to fill in the gap of the low temporal resolution of synthetic aperture radar. I do want to mention that satellites can be used to assess flood risk, not just flood monitoring. So by using a derived flood map, we can create sort of a global or regional assessment for the number of days that a given area is flooded. This is an example over Africa. Could be done over a given year, could be over 5 years or 10 years. The idea is this can help and is helping assess where the most flood-prone regions are and help with flood mitigation, preparedness efforts, determining where to locate buildings, schools, and other infrastructure, and things like that. Currently, NOAA has a derived optically based VIIRS daily and 5-day composite from 2012 to 2020, as well as from September 2023 onwards, to help begin this effort, and is making this data freely available to users for analysis on AWS. The data from the intervening years from 2021 to mid-2023 will be reprocessed and hopefully in the near future. There's also there's an offline archive that is accessible to provide that data from the gap here. So in summary, optical, SAR, and blended products, flood extent products, have been developed with the NOAA LEO flood product currently running in operations. There's an archive of the native resolution 375 meter VIIRS product, which is currently available on AWS, as well as in an offline archive. And this archive has been used by numerous agencies to assist flood mitigation, as well as its impacts. UNISAT, the World Food Program, and other international organizations routinely use the NOAA flood product to map flood extent during extreme flood events to determine impacts on population and crop loss. And finally, the interaction with the U.S. National Weather Service, River Forecast Center, National Water Center, other agencies, such as the World Food Program and others, are key in knowing what to provide the users for satellite-based flood monitoring. Thank you very much.